Okay, class, welcome back. And this is the initial welding problem. And last time we mentioned some very important research about the uniqueness, existence, and the small change corresponding to the small perturbations to the initial welding problem. So first, this is the setting for the initial welding problem. And we have stated that this is the very important things from the last class. That is, say, we assume that the function is continuous, which means that it's continuous on the t variable, it's continuous on the y variable, and the f function is also continuous on the d in the on the d domain. This is the two-dimensional space, a subset in the two-dimensional space, and in this function is Lipschitz continuous in the variable y, and in this assumption setting, and then we have the initial value problem, and then it is well posed. And this is the things, and then I draw the subset D here, the examples of subset D, and then it could be a long region on the plane. And this is a uniqueness and existence and the small change towards to the small perturbation. And I mentioned that we can apply the numerical methods to not all the numerical methods. So some numerical methods can treat the Euler problem, but here in our class, and then we will treat the we only treat the well-posed problem with the following methods. We would learn one method today that is called the idea. It's called Euler's methods, and then the Euler's methods is based on the Taylor expansions. And so let's see. And you have already seen the derivative y on the derivative of y function, and regarding to t variables here. And does this remind you something from the 104b? So if you want to approximate a function derivative, and you would use finite difference method, right? Finite difference methods, you can use either, let me see, you can use either the forward Euler method or the backward Euler method or the center point methods. And then you have a lot of ways to approximate the derivative. But now you will see at the end of the day, the things is quite simple, and then you are just applying the Euler's, the backward Euler's or forward Euler's methods to calculate the derivative on the left-hand side here. And on the right-hand side, and then you just calculate the same. And but today we are going to divide the whole things with the very beginning, the very initial idea, that is the Taylor expansion. Wow. Oh, that's not good. I found out that I haven't mentioned the sequence method again after I proved the convergence theorem for the sequence method. Okay, but let us get back to there once we finish these things. Let's see. only I just pick a wrong lecture notes and then find out that I haven't finished that things. So now the things we do is quite similar to what we have in the numerical methods for the differentiation. So for the first step, and then we are going to participate the whole domain into the mesh format. So here I'm going to y function. Y function is a function of the variable t. This is just this is a function with single variable, and now what's the domain for the t? So in this setting, in the assumption setting, the t is in the domain a and b, and so we are going to divide this domain AB into several subinterval here, and it should be, so here we are going to divide the AB interval into n subinterval. Equal length subinterval here. And if we divide this AB interval into n subinterval, and then we have n nodal points, n plus 1 nodal points, and they are, you have n plus 1 nodal points, and the nodal points are, so we are dividing the domain for the t. So that is, we have the ti nodal point, and then it equals to the a and then plus I h, and where the I can be for each I equals to 0, 1, 2, and then to the n, because we have n plus 1 nodal points here. And what's the step size? And that is the length of each subinterval, because here we have n interval here, n subinterval here, and then which means that the h, where the h is just the b minus a divided by n. And let me write down the things here. So that is just, we are dividing the interval a and b, and then into n subinterval, and then where we put the this one to be t0, and then t1, t2, and then all the way to the, so the last point is just the tn, and that's the the right endpoint here, the tn. And this is the first things we need to do for the Euler's methods. We we partition the intervals into n subinterval, and then now I'm going to do some Taylor's expansions towards to the point ti plus 1. So the idea here is, let's use the Taylor's theorem, to expand to get an Taylor expansion at the point ti plus 1. And which means that we can have a lot of expansion here around each point here. each point on the axis. This can be the ti plus 1, and then this could also be the ti plus 1, and then we are going to do the all these Taylor expansions here, and but we can just write it in this way. And we also have, let's see, do we have any assumptions before this? So we only assume that the y is continuous, and then the y is Lipschitz continuous in the variable y on the domain D, and then before this. But here I'm going to add one more assumption here, and then we are going to suppose the y function. We have some assumptions on the f functions just now, but here we make some assumptions about the y function, the regularity about the y function, and then let's suppose that the solutions y, that is the unique solution. So to the IVP problem, and we suppose this unique solutions has the following regularity. So let's suppose that it has two continuous derivative on the interval AB. And then now we are going to do the Taylor expansions for the point, where the I equals 0, 1, 2, and then all the way to m minus 1. And we are going to get the ti plus 1 here on the left-hand side. And then on the right-hand side, we are doing the Taylor expansions around the point ti. So this one, yti. So before I write down the whole Taylor expansion, and then I would like to remind you of the Taylor's theorem, in case you forget what we have here. That is the fx, and then equals to the sigma sums in, and then r equals to 0. Let me just use a small n here, and then it should be f a, and then I here. There's something weird. I get used to the k index here. F k, and then k factorial x minus a, and then k factorial, and then the remainder is f k plus 1, and then cos c, and then k plus that should be the n plus 1, n plus 1, n plus 1, and then this one is axa, and then n plus 1. But here we have the function, it's y function, and then the x is the so here it should be n plus 1. So now in this Taylor expansions theorems, and then we let the f function to be y function, and then we let the left-hand side x to be the ti plus 1 here, and then we let the k, we let the a to be the ti in our setting here. So also because we assume that we have two continuous derivative here, and then which means that we can have this one to be the f second derivative, and which means that the n we set it to be 1. And so now we set the n equals to 1, and then let's get the Taylor expansions here for the y function, and we got this. So this is the first item, and then the second item should be the y derivative, the first derivative, and then evaluate at the ti, and then doing the factorial divided by the 1 factorial, and then that is just divided by 1. And so that is just the y derivative here. And we have the x ti plus 1, and then minus a, and then that is ti. And the last one should be the irritant. And then the irritant should be the second derivative, and then you evaluate at the point, and then I'm going to denote it as ci, because for each small subinterval, and then the c could be different. And then here, this is the second derivative, and then you evaluate at the ci, and divided by the 2 factorial, and then the 2 factorial is just 2. And we have 2 here, and then ti plus 1 minus ti, and then doing the square. And this is the Taylor expansions. And now for this ci is something's in between the ti and ti plus 1. And because we have already just said our step size h is just b minus a divided by n, and then we can also have the h step size is just the neighbor node voice, and then subtract the another one. And because this, and then we have the yti plus 1, and then equals to the yti, and then the second item is just the first derivative, and then times the h minus the second derivative, and then times the h squared. And here we have this is the what we have here. And also we need to record that what we have in the initial value problem. So we are solving such an initial value problem here, and then that is dy dt, and then equals to the f ty here. And this is just the first derivative. And we are going to substitute this, replace the things with this equation. Because the first derivative equals to ti. Do you have any paper here? Let me wait a moment. I'm going to get some paper. I believe this is spring, and then I get some allergy from the air. And let's go back to our discussions. And then we have, this is the initial value problem we are solving. And I'm going to substitute the function, the equations into this derivative y. And I got this because this is the first derivative of the y, and then it's just equals to the f, and then you evaluate at ti, and then y ti here. Does that make sense? So this is just from the initial value problem, and then I just get this one. This one is just y by p, right? And then I just substitute the ti here in this equation on the left hand side and the right hand side, and then I substitute ti, and then which means that the y prime ti equals to the f ti y ti. And this is the things we get here. And so what do we have at the end? So now the things is that if you have a small step size h here, then actually this is a small error. So we are going to approximate this equation and then by ignoring the last item. This is something similar to what we did in the numerical methods for the differentiations. We do the Taylor expansion and then we skip some items at the end. For the we skip the error items and then we just use this formula to be the approximations to this formula. And so now for the Euler's method, it's just skip the last item. So let's delete this. Delete this item. And then we got to this. This is the Euler's method. And then we delete the last item. And then then we have the Wi, and then the Wi is just the approximation of the YTI plus 1. And then the Wi satisfies the following, Wi is just the approximations of the Y evaluated at TI notables. And then the Wi is satisfied the equations looks like this. The Wi plus 1 and then equals to the Wi and then plus F and then TI and then YTI is just the Wi because we use the approximations here. And this is the things we have and then times the H. And this is the approximations. We just delete these items and then we get and we let it to be the equal sign and then we replace C. So the Wi is just the approximations of the YTI here and then we replace everything here one by one and then we get to the Euler's methods. And as you can see here, this is just the one equation and then this is the equations in the initial value problem. But initial value problem, which means that we also have the initial value. And so this is not the complete setting. We have another equation here, or the expressions, the equality here, and then it's just the W0. And then which means that this is the approximations to the their initial point, but actually this one is exact because we set it to be the initial value to as the original initial value problem. So here we have the I and then it's from 0 and then to the n minus 1. And this is the Euler's method. Euler's method is just a Taylor expansion and then skipping the last item, and then the last item is just the error in the Taylor expansion, and then we get to the Euler's method. And then we solve this system, and then we get the approximations to the values for the YT0, YT1, and the YT2, and then to the YTN. And this is the things we have here, the Euler's method. And I'm going to show you one example. And so let's see. There's one example here. I'm going to keep this one here, and then going to give you one example how to approximate the whole things with the Euler's methods. So here we have a function initial value problem, and we have this y prime and then equals to y minus t squared plus 1. And on the t interval, the time interval is between 0 and 2, and the initial point, and then it's 0.5. And now I'm going to give you one thing here. We let the h step size, let's set the h step size to the 0.5 in this example one. And let's see. So for the solutions, we got this. So we are going to solve the approximate the YTI in this way with the formula above. And then the W0 is just the initial value we have in the problem setting. And then for the W1, it's just the W0 and then plus, and this is my f functions for this problem. And then this is the f function, and then ti, fty, right? And then so if I do the plotting, fti and then wi here, and then I would have, so which means that I'm going to write out the whole things here, wi plus 1, wi, and then so because we have the f function here, and then it should be the y function, and then that is yt, right? And then evaluate at the ti, and then that is just yti, right? This one, this is the y function yt. And then if it is evaluate at the ti, and then that is the yti. And the YTI, we are going to use the WI to approximate it. And then for the T function, we have the TI here, and then square, and then plus 1. So at the end of the day, actually you have, let me see, am I right here? Is there anything wrong here? So there is also the step size, and then the step size is 0.5. And so at the end of the day, you have 1.5 Wi, and then minus the Ti squared, and then plus the, there's a coefficient here. It should be the 0.5. And then plus the 0.5 here. So at the end, you have for the first one, the W1, it's just the 1.5, and then W0, and then minus the 0.5, and then that is the T0 squared, and then plus the 0.5. And here we have, that is just 1.5 times the 0.5, and then 0.5. And I like to remind you of the nodal points we have here. This is the domain, the time domain 2 to the 2. And we are dividing the whole domain into 4 subinterval with the step size 0.5. And actually we have here, this is the nodal points 0.5. And then this is 1.5. And our T0, the T sequence are beginning with the T0 equals to 0. And then this is T1, T2, T3, T4. And I would like to remind you of the formula for the Ti plus 1. Ti plus 1 is just the Ti, and then times the plus the H. So, or you can also have another way to calculate the things, and then that is the I plus 1 and then times H. And so here, the T0 is just 0. This is for this example, this formula. But if this is not the things in this, if the setting is not from 0 to 2, and then this one could be I plus 1H, and then plus the left endpoint A. And so let's go back to this question, and then the T0 is equals to 0. So we have 0 squared and plus the 0.5. So at the end of the day, you calculate all the things we have here, and then you would get to, let me see. So the first one, it should be 0.715, and then plus the 0.5, and then we get to the 125, And then this is the W1, and then W1 is the approximation. So I would just write that down. This is the approximations to the YT1. And we get to the approximations to the YT2. And the YT2 is approximated by the W2. And then the W2, and then from this formula here, and now we got the W2, and that it equals to the 1.5 W1, and then minus the 0.5, and then T1 squared, and then plus the 0.5, and which equals to 1.5 times 1.25 minus 0.5, and then the T1 is just equals to 0.5 here, and I got 0.5, and then square, and then plus the 0.5. So at the end, let me see, am I right here? Yes, I'm right, but there's some number here I should be very careful about. Let me see. So at the end, if you calculate all the things with the calculator, actually you would get to this number. And then let's say you are using the calculator, and then you get this number 2.25 here. And for the Y23, Y evaluate at the time T3, the nodal point T3, and it's actually approximating by the W3, and then W3 is calculated by the 1.5 W2, and then minus 0.5 to T2 squared, and then plus the 0.5 here. And from the last equation, and then we have the W2 equals to 2.25, and minus the 0.5, and then T2. The T2 is the number 1 here, and then we got 1 squared, and then 0.5. And this equals to 2.25. No, 2.25. Let me see, it should be 3.375, and then by the calculator, it lasts, and then we get to the approximations T4, and which is the end of the time, and then that is 2, and it's approximated by the W4. And the W4 is just a 0.5, and then W3, and then minus 0.5, and then T3, and then square, and then 0.5 here. And for the T3, and then it's just the point at 1.5. So here we got 1.5, and then W3 is just the 3.375, and then minus 0.5, and then the T3 is just 1.5 squared, and then plus 0.5. And at the end of the day, you use your calculator, and then you get to this number, 4.4375. I believe that we have, this is the final result for this question, and then you will see we are just repeatedly using that very beginning equation, and that's things we derived here. We have the Wi, and then this is the f function, you value at the Ti, and then Yi, and then times the step size. And this is Wi, and then you write down such an equations from the Euler's methods, and then we repeatedly apply the equations to the W1, W2, W3, W4. Does it make sense? Any question here? How to apply the Euler's methods to one example? So there's one thing. Let me see. Am I doing the numerical example here? Yes, actually, I'm going to give you another numerical example. So this is quite interesting, these things. And then I will let you to do some coding for these questions, because this is a very general method to people use in the numerical methods to get the approximations of the initial value problem solution. So let us see, there's one example here, and then I will let you to observe something. It's about the error. So this is the things we have here. And let's say we are going to get a smaller step size. And let's say we are going to get the H to be 0.2, and which means that we have 5 subinterval, a 10 subinterval, and you would get this at the end. So before I move to the calculation part, and I would like one volunteer here to write down something similar to this. Now, what is the updating rules for the step size H? And then equals to 0.2. Is there anyone here to be the volunteer to write down the updating rule? Wi plus 1 and then equals to 1. No one? No one? Oh, I should give you some benefits to do so, right? Bonus point. Any volunteer to get the bonus point now? No? Okay, I will get the bonus point here. I will get the bonus point, and then please give me like 10 points. And here we have, let's see, I just write down on the iPad in this case. So you have your f function and then t function and y fty here. And then if the h step size, we just change the h step size. And then if h equals to 0.5, 0.2, and then what's the wi plus 1? I plus 1 is just wi, and then plus this is the f function. Let's see. So on the right hand side, this is f function divided by ti and then wi, and this is fyt and then minus t squared and then plus 1. And so for the yt on the right hand side, and then you just change it to be wi. So this is the same wi minus ti squared and then plus 1. And that is the things here. Because this is yti, and then we use the wi to approximate it. And so on the right hand side, we have wi and then minus ti squared and then plus 1, and then times. Now we change the step size to the 0.2, and that's the things. At the end of the day, we are just updating one small things here, and then we change the coefficients, and then that's 1.2, and then minus the point. Oh, there's another change here. It should be 0.2 and then ti squared, and then plus the 0.2 here. Does it make sense how to get the updating rule here if the step size is 0.2? Okay, I get the 10 bonus points. Thank you. Thank you to give me such a chance. And never mind, let's get to the next part. We are going to take a look at the numerical example here. You have, oh, this is something I need to read. It's not something you need to look at. And so let's get back to the numerical example here. So there is another example. And this is a numerical examples on the textbook, and then it's with the step size is with the step size n equals to 10, and then here the step size is 0.2, and we just derive the whole things for the this is 1.2. Yes, it's correct. One W.2 here, and then Wi here, and this is because this is Ti is just equals to IH, and then H is equals to the 0.2, and then so the 0.2 square, and then you get 0.04, and then I square, and then plus 1, and this is another detailed calculation here. If you want to get to the formula in terms of I, and but you can still write the very beginning one. And so here we use this formula to update the Wi plus 1 value. And for example, is just we have W1, W2. But actually, you can just stop writing the whole things up to here, up to here, and then change the H to be the 0.2, and then that's it. And you update the whole things with this formula, and then you use the computer, and then use the Euler's methods algorithm, and then to compute all the value here. And this is the W0, W1, W2, W4, and then this is W10. And this is the true solution, the value at the time, the nodal points time, Ti. And this is a true solution, and this are the error. And now I will give you like 2 minutes to observe the value here. And could you tell me some things about the error? So at the very beginning, and then what's the error? Is 0, because we set the initial value, and then the W0 to be the initial value, right? And you will see this things is becoming bigger and bigger. Do you see this happening to this reference sample? And actually, this is not some things happen to this just to this example. It happens to any numerical methods to the initial value problem. So at the very beginning, you have a small error, but the error could propagate, and then it would become bigger and bigger at the end. And this is a numerical method for the initial value problem. And then, so what is very important is that when you see one problem, and then at the end, and then you would expect the error at the end is bigger than the things in between. There are errors in between. So let's see. There's one theorem about this. Let's say there's one theorem here. It's about the error of the Lipschitz of this Euler's method here. So let's see. This is the theorem, and then you will see in the error term, and then why this is getting bigger and bigger. So here, this is a theorem, and then we are not taking the time to prove this theorem, and this is a theorem 5.9, and we have several assumptions here. We have first, we need the well-postedness of the problem, so we have f is continuous, and also Lipschitz continuous. Continuous with a constant L. And then on the domain D, And this is the domain I give you. And then this is a strip on the two-dimensional space. And then is the time is in between A and B. And then but for the y variable, it could be the whole real axis. We also assume that, so from the derivations of the Euler's methods, we have something about the second derivative. And then here we are going to have some assumptions and on the second derivative of the y function. And we suppose that there is a constant m, and then that is the bound for the second derivative. And this makes sense because otherwise, if the second derivative is very large, and it could be the error returned in the Lagrange meter could be very large. So if we want to skip that, ignore that error item in the Taylor expansion, and then we should have some bound for the second derivative. And then the Euler's methods, we say Euler's method has the following error here, has the following error. And I would like to remind you of the yi, yti, and then that is the true solution part. And evaluate at the time ti, and then wi is approximation of the yti. And now the error return is given by this yti, and then this is true solution, and then minus the wi is the approximation by the Euler's methods, and then it's bounded by the h, and then there's the m here. M is the bound for the second derivative, and then 2L. L is the Lipschitz constant, and then you will see there's another constant on the right hand side, and that is the L, and then Ti, and then minus the A. A is the beginning point of the time interval, and then minus 1. And now let's focus on this item, Ti minus 1, Ti minus A here. And you will see this is why we have a larger and larger errors throughout the time, when the time is becoming bigger and bigger, because when we increase the Ti number here, this numbers would be bigger and bigger. And this is why the error is increasing. If you are doing it, analyze the whole problems in an analytic way. And then you will see these items actually explain why we have a bigger and bigger error when the time is becoming bigger and bigger. Because this one is increasing. And any questions about this theorem here? We have several assumptions, and it's about the f function's continuity, and then Lipschitz continuous, and then we have the bound for the second derivative, and then we can write down the error terms in this way. And this items explains why the error is becoming bigger and bigger. Any questions? No? Yes? No? So if you have any questions, then you can come over here. And then we are going to get to another part of the numerical methods for the IVP next time. And it's also based on Taylor expansion, but we keep more items in the Taylor expansion. And that is the higher order methods for the initial value problem. Okay, pass this over. This is the introverted question part. Okay. Law tridiagonal. So how should we do this? 开答应该没有，应该就是这里应该是感觉零的，但是你这个东西应该是够小了吧？哎，这是 homophone 吗？啊，
我好像对了答案。
那是啊，哦，这样子吗？你可以把那个答案也打开一下下吗？我对一下，然后我再把送回去。可以从另外一个 tab 里面，然后同时打开。哦，不能。你先打开一下下，我看一下这。
Question here, like what's the number diagram for W4?
It's just step 4, and then it's C.
I think you wrote 4 point something. I didn't see that part.
Let me see. It should be 4.437.
I think it should be 3 point.
3 point. Let me see. Do you calculate it?
It's W3 is 3.375, right?
Yeah.
And this part is only 0. Why is it 0.5 here?
Let me see. There's something wrong. There's something
This
wrong.
one should be W3, right? It should
Yeah.
be 3.375 here, 0.5.
Yeah, it's 0.5.
Why is it 0.5?
That's because at the very beginning we have this formula here.
Yeah, here's 3.375 times 0.5.
Yeah, 0.5 and then ti squared. Right?
Ti, so we have T3, right? T3 is 1.5.
Yeah. Yeah.
1.5 squared. Okay, I will double check that.
Let me double check that on the computer. I'm going to calculate a while here. Let me see. There's something.